Now, there's something interesting. For example, in classical physics, is that if I give you a potential, you can always add to the potential a constant, right? So because in experiments uh, we don't really measure potential. What do we measure?
Force.
Force, exactly. But if I were to reformulate that in terms of potential, what would we measure? We measure potential difference, right? So if we add, say, a constant to a potential, then in the potential difference, that constant does not contribute, right? And that's why we can arbitrarily assign, say, 0 potential energy to a charge at infinity, right? Because, we are adding some constant. So that's a kind of an ambiguity in the potential. But it turns out, and this is something I want you to show because it's a fun exercise to do and very, very easy, is to show that Maxwell's equations actually it's, yeah, or Maxwell fields, I should say, say B and E, remain the same. When we try to be fancy, we use the word invariant. Under the transformations, under the following, transformations of phi and A. So if you replace phi by, say, phi minus 1 by C del lambda by del T, where lambda is some continuous function, and A by A plus the gradient of lambda, then it's a one-line exercise to show that E does not
So
change.
is lambda just a function of t? I mean, space
No,
independent?
no, lambda is a function of space and time, okay? It's a scalar function. Okay? Then it's just a one-line exercise to show this, okay? And you should show it for by yourself. So these give rise to the same physics, whether you use phi or phi plus these things, right? Physically, they are the same. So this set of transformation have a name. It's called gauge transformations. Okay? Okay, any questions so far?
No, sir.
Okay. So let me conclude by a few comments, and next time we will show how these gauge fields and gauge transformations are important in quantum mechanics. But let me just make some comments here. So when we're doing classical electrodynamics, we can either use phi and A, or we can use E and B. Okay, so it doesn't. So this in this alternative formulation, of classical electrodynamics in terms of phi and A is a luxury and not a necessity. Okay. Number 2 comment is that, however, in quantum mechanics, the wave function of the charge couples to phi and A. Therefore, in quantum mechanics, the use of phi and A is is more essential. Okay. So this is something we will see in the next. So it's analogous in the next lecture. So this is something we'll see in the next lecture, and it's somewhat analogous to how in classical physics you can use complex numbers to do a lot of elegant stuff, right? Write down, say, solve Maxwell's equation or any oscillatory problem very, very easily. It's a powerful method. People who are doing electrical engineering, they use a lot of complex numbers. But it's a very elegant and very powerful trick. But in quantum mechanics, you cannot even formulate quantum mechanics without complex numbers, right? So it's a little bit, in my mind, analogous to that. So the third comment that I have to make is that you can choose phi and A to solve a problem, or you can choose phi prime and A prime, where the latter is related to the former by a gauge transformation. So these are physically equivalent. So this should be prime. So phi A and phi prime and A prime, use a bracket, are physically equivalent, okay? So whether you use one or the other is a matter of convenience. But the choice of one set of phi and A is called a gauge choice. Okay. So let me give you an example. And let's conclude with this example. So consider a magnetic field which is in the k direction, a constant magnetic field in the k direction. So Bz is constant, okay? Now, if I take one of the gauge fields to be AX is say minus B ZY by 2, AY is minus plus BZX over 2, and say AZ is 0, then using the fact that B is curl of A, so you guys know how to compute curl, right?
Yes, sir.
So you have something like I, J, K in a determinant, and you have D by dx, D by dy, D by dz, and here you have AX, AY, and AZ. So if you use this and these values, then you get you'll basically get this thing, right? So this is a choice of a gauge. Another equivalent physical configuration that gives rise to physical configuration, but a different choice of gauge, is say A prime of X, where it is minus BZY. AY prime is 0 and AZ prime is 0. You can show that it gives rise to the same B. Okay. So how are these two gauges, gauge choices? They're called gauges for short. How are these two gauge choices? Well, actually, no. Yeah, gauge choice and gauge is different. How are these two gauge choices related? Well, phi is related to phi prime. So here, phi and phi prime are the same. But on the other hand, A is related to A prime by, if you take A and subtract it from it, the gradient of some scalar function. That scalar function happens to be Bz x of y divided by 2. Then you can show that this gauge transformation relates these two gauge choices. Okay, these two gauge choices. Okay, so I think I'm going to stop there for today. Any questions?
No, sir.
Okay, have you guys? How many of you have seen the vector potential before?
Yeah, I did last year during the CAD course.
Okay, anyone else?
I did in the same course.
Okay, so you guys saw that. Okay, so it's not completely, but you probably didn't see its application in terms of quantum mechanics, right?
Yeah, I didn't see anything about that.
Okay, so we'll get to that in the next lecture. Okay, any more questions?